This is methane, CH4. Methane, natural gas. How many atoms in all are present in methane? Did we learn that this week?
No, but I can tell you.
Okay, go.
Besides 5.
Oh, good. 5. So there's 1 carbon atom and there's 4 hydrogen atoms for a total of 5 atoms in 1 molecule of methane. So, terminology there. 1 carbon atom, 4 hydrogen atoms gives you 5 total atoms in 1 molecule of methane. Okay. So the law of definite proportions tells us that every compound has a recipe. If it's methane, then it's always going to have 1 carbon for every 4 hydrogens. So if you have a big pile of methane, there's always going to be a ratio of 1 carbon to 4 hydrogens. 1 carbon to 4 hydrogens. Always the same ratio, or it's not methane. And next week, just to give you kind of a heads up, since apparently the reading assignment was strange this week and it didn't quite cover all the things that I thought it did, you're going to learn another law, the law of multiple proportions. So the law of multiple proportions actually is even worse. When you read the law of multiple proportions, it almost feels like it's saying gobbledygook for me. It says a fixed amount of an element that can combine with another element in more than one way will do so in whole number proportions. So how to apply that to real life, well, that seems a little bit complicated, but it's really not. What it means is if you have 2 compounds, 2 different compounds, always going to put different, that are made of the same element. And here's a caveat, and you keep the amount of 1 fixed. There is a relationship between the others. Oh, thank you. That is a whole number ratio. So maybe I just said gobbledygook like I said but I'll show you. This will help you next week too if we just kind of cover this briefly. Okay, so the law of multiple proportions says you have to have a whole number ratio even if you have 2 compounds, but they have to be made up of the same elements. So let's look at methane again, since we're kind of going with that. 1 carbon, 4 hydrogens. Well, carbon and hydrogens love to bond together in many, many ways. Hydrocarbons, stuff we eat, every type of fuel. Let's see. So we'll just take the next kind of most simple one. So carbon, C2, that'll bond with 6 hydrogens. So if you have 2 carbon, that'll bond with 6 hydrogens. Okay, so now we have this fulfilled. 2 compounds that are made of the same elements. Okay, there's carbons and hydrogens. Here we've got 2 carbons and 6 hydrogens. Okay, so we've done that. Now, if you keep the amount of 1 fixed, well, there's 1 atom of carbon here and 2 here, and 4 atoms of hydrogen and 6 here. So there's not a place in these 2 where we can keep the amount of 1 of the elements the same. But if you notice C2H6, that can get kind of reduced, right? Like if you had the fraction to 6, you could reduce it to 1/3, right? So I can kind of This is not to say that the molecules change. The molecule is still going to be 2 carbons and 6 hydrogens, but you can look at the proportion there. So now this would fulfill this requirement here. Keep the amount of 1 fixed. Well, now I've got 1 carbon and 1 carbon. I can compare, right? Then there's a relationship between the other elements. Okay, so let's look at the other elements. Well, here, for every 1 carbon, I have 4 hydrogens in methane. Right, so methane has 4 hydrogens if there's 1 carbon. And here, this is ethane, so I have 3 hydrogens for every 1 carbon. So, you can see that there is a whole number relationship between things that are made of the same elements, as long as you keep the amount of one of the elements fixed. So, that's how the law of multiple proportions works quickly, just so next week it's not so very confusing. But I'm actually going to let you have a second with that, and then I'm going to get rid of it, because there's an important point you need to understand before the lab here with the law of definite proportions. This is a test question. The law of conservation of let's see here. Matter cannot be created or destroyed. Alright, so the key point for the law of conservation of mass here is every atom that, and this is a key point for the lab, key point for the test, this is the big guy today. Unless we're talking about a nuclear reaction, every atom that enters into a chemical reaction, RXN means reaction, is still the same type of atom. At the end. Right? So here, this lie, every sodium atom is still going to be sodium at the end. Every oxygen will be oxygen at the end, and every hydrogen will be hydrogen at the end, and they'll all still be there at the end of the reaction. Not one atom will be destroyed, not one atom will be created with any chemical reaction that we do. Not only nuclear reactions can do anything like that. So, when you look at the law of definite proportions, that every compound has a recipe, and the law of conservation of mass, that every atom that goes into a reaction is still there at the end, exactly the same as it was. Now you rearrange their bonds with each other, but they don't change. Then, these two things are really where the idea that there are atoms came from. This is the test question, okay? These two laws, from these, Dalton hypothesized, how would you say hypothesized that there are atoms. Okay. I mean, if you think in a time before people knew there were atoms, if you think back, there was, at first they just thought that matter was like a sheet of aluminum foil. You roll it out, and it's just a big long sheet of stuff. You cut it in half, you just have half as much. Cut it in half again, half again, half again, half again, half again. And you could just keep cutting the roll of matter in half over and over and over again. You could always get half, right? Just like a sheet of paper. You could always cut that in half, always cut that in half, always cut that in half. But when Dalton looked at this and found this really happened every time he ran an experiment, and this, the law of conservation of mass. That every time you do an experiment, it weighs the same at the beginning and at the end. And he said, maybe there's a point at which I can't cut it in half again. Maybe there is the smallest piece of matter. And that's an atom. And it's important for the test that you know that these two laws are the driving force behind Dalton's theory that there are atoms. Did you read about Dalton this week?
No,
No,
but it was
it's on the next page.
I just scanned the page for the view
read.
questions, that's all I did.
Okay. I can't figure out what you guys read this week. Alright. Well, that is lots of information there. Did we talk about the periodic table and metals and non-metals?
Yes.
Yes.
Okay, good. We have something to talk about. That's great. Let's get a periodic table out then. One that we can all use. And also, this four periodic tables are kind of a disaster.
Wow.
All right. So this one's colored differently than the one in your book. Of course, every periodic table that you ever work with will be a little different than the one in your book. But you really need to get familiar with how to use the copy that you're allowed to use on the test. So you want to look at that one every time you do your homework pretty much from now on. And when you look at the periodic table, did it talk about what all the things mean on the periodic table at all? Any of that? Just how to find metals and non-metals?
Yes.
Okay. So, metals and non-metals. Hydrogen, even though it's sitting right over here on top of this lovely stack of metals, is a non-metal, and really it should go right here, number 1, hydrogen should go right here next to number 2, helium, be a non-metal, and be happy. But you'll learn later, because it has 1 electron, and it can bond with that 1 electron, it behaves like these other guys that have 1 valence electron, which you don't know about yet. This is the hardest class until at Module 6. You don't have enough vocabulary to explain why these things are. But anyhow, hydrogen's like a non-metal. It'll go over there. These 2 columns here are metals, and then this like short stack of stuff in here, these guys are transition metals. That means that they can bond in several different ways, unlike these guys that only bond in kind of one easy, plain way. So we have to tell you kind of extra information about these metals before you know what to do with them later in the year. Or you have to figure out and do extra work about them before you know what they're actually called. And then you see this heavy line on your own periodic table, which doesn't appear to be on my periodic table, but there's a color change at least. So between aluminum and silicon, between germanium and arsenic, between antimony and tellurium, polonium acetine, we've got this heavy line, and that divides the metals. These are transition metals and regular metals, but they're all metals. And that divides the metals from the non-metals. You can see the non-metal group is quite small, but all of the things that kind of make us alive are in the non-metals.
Except for chlorine.
Well,
Chlorine kills us.
true, but I mean it does serve a function.
In swimming pools.
It keeps us safe, right? But things like carbon, nitrogen, oxygen, kind of the building block of life, hydrogen, elements are non-metals. But of course we need lots of metals to do their jobs in our bodies too. But our big structure is kind of built of a lot of non-metals. So metals, and then this tiny group of non-metals. Now, all of these light blue guys here on the end are also non-metals. Your periodic table keeps them the same color as these. There are different colors there because they are so completely unreactive. They don't actually do a whole lot of chemistry. They're the happiest elements. They don't want to react because they're perfectly happy the way they are. And I'll teach you more about that later. But so they don't really participate in chemical reactions easily. So mainly these green guys are the ones we're going to use, but these are non-metals too. These guys down here are also metals, but they are more complicated. When we teach you about electrons and bonding, these guys have, never mind, too complicated. You won't have to deal with these guys even when it comes to electrons and bonding. So I might tell you about them, but you won't have to do it. So metals, non-metals. That is very important for next week. The stuff you read next week, hold on, is going to teach you the difference between ionic compounds and covalent compounds. And that might be a little confusing, so I'll give you kind of a preview of that too. Ionic compounds have at least one metal atom in them, except for there are a few exceptions. Always exceptions. But for your purposes, especially for this test, this is what you want to remember. One metal atom, and then some non-metals. One or more non-metals. And then covalent compounds, all non-metals. Okay, so if there's a metal in the compound, any of these transition metals, regular metals, any of these guys down here, it's ionic. If it's all non-metals, it's covalent. So they are named differently. And next week we're going to talk about naming them, but since you have to do your homework this week, I'm just going to give you that preview that covalents use a bunch of prefixes, like di or tri or tetra, like to tell how many things are, how many atoms are present of each type. Ionics don't use prefixes, even if there's several. Here's a key point for your homework. Don't use prefixes if there's a metal present in the compound. Don't use prefixes for ionic things. Don't use prefixes for ionic things. And like by module 13, you'll have like kind of forgotten this, and then you'll use a prefix for an ionic and get it wrong. So this is like not just for this module, this is like forever, big deal. Ionic compounds don't use all these cute little prefixes. Only covalents do. So that's a key point for your homework, and it's something that tends to confuse people, at least at first. Alright, so let's do a lab, and then we'll take a quiz, and then we'll go over some questions. Alright, so I'm using eyedropper, and so, just like I was saying, sometimes it can be a real challenge to start communicating chemistry when you haven't had a ton of experience yet, and that's fine. This is kind of how you get it. But this reaction that we're going to study today is an acid-base reaction. And probably, if you took physical or general science, you've seen some acid-base reactions before. And anytime you mix an acid with a base, you get a chemical reaction. Can you think of a famous one that everybody does in science class?
The baking soda and vinegar.
Baking soda and vinegar. So vinegar is
The acid.
and baking soda is
Base.
Base.
Okay. And when they come together, what happens?
Yeah, CO2.
Okay.
No.
So in this class, we don't study acid-base reactions till like module 10 or something. I know. So it can be a challenge to understand the point of this lab, because what you see, the fancy color change, ooh, look, something happened, is not the point of the lab. And so that can be a little frustrating, and a lot of people give me their first draft of a lab report, and they see the pretty color change, and they know that it was an acid-base reaction, and all that is totally true, but it's not the goal of the lab. So, the goal of this lab is to learn about the law of conservation of mass. But you don't have to write that in. We're going to write this lab report together, so you won't have to have any homework with it or anything. So, this, anyone know what the purple stuff is?
It's red cabbage juice.
It is, and it smells really bad, and we will attempt to get rid of it very quickly.
Do you want me to turn on the fan?
Yes, please. That would be great. Very good idea. Okay, so purple cabbage juice is what we call an indicator. An indicator is something that is one color in the presence of acids and another color in the presence of bases. I'll pull out the water here now. So, actually I can do this. I don't particularly want to see the water on my scale. So what I'm going to do here is just try to give you kind of an idea of what you're seeing with the color change so we can get that out of our systems and then kind of realize that this is not the point of the lab. So this is not actually the lab, this is just me showing you stuff and throwing this out the window. This will be my little holder. Alright, so I have 3 test tubes. I put a little water in 2 of them, and I put a lot of water in 1. So, in the presence of neither an acid nor a base, but just water, which came out of a still water jug, and we really hope is neither acid nor base, but a perfect neutral pH of 7, this indicator appears to be purple. In the presence of an acid, such as vinegar, which I'm just diluting with a little water here, just so everybody's kind of the same. Put a little vinegar in. Vinegar is an acid. Our cabbage juice. Anyone want to make a prediction? Pink. We can see it's much pinker in the presence of the acid. Stirring with a test tube, you just firmly pinch and whack your test tube, and it creates a little vortex. You'll all get chances to practice stirring with test tubes. So you can see the indicator shows the acid to be much pinker. Neutral is purple, acid is pink. And in the presence of this strong base, which when you use, oh, we should all put on goggles, because the vinegar isn't scary and the water isn't scary, but the sodium hydroxide is not awesome to get in your eye.
I don't want soap coming out of my eye. It's fine.
Oh, I'm not going to give you this one because that's too fast.
So if I
Don't burn yourself.
It is.
I'm not afraid of the lye. Actually, I've gotten my hands dipped in lye lots of times. I probably should be more afraid of it than I am. So I put a little bit of lye here in a test tube. Stir it in. And what color do we predict? Anyone remember?
Blue or green.
Blue or green, depending on exactly how basic it is. And since lye is incredibly basic, we did green. It's really green.
Ammonia works too. Makes
Yes,
it
ammonia is nice and green. We'll use that for the titration lab because it's
It's
already
turning yellow.
Yeah, it's really, really basic. And even if I add a bunch of vinegar, maybe we'll get to blue, just so you can see the full range. So green is really, really basic. Still really not going to give us anything. So if I dump it out, even just the inside of the test tube is probably so incredibly basic that but I'll let you kind of just see the whole range of cabbage juice. Oh wow, that tiny bit of lye didn't do it, so maybe we can just sprinkle 2 crumbs in and see blue. Oh, you can see the tip is green where the lye is kind of settled down. But I definitely want to get the color changing out of our system so that that is not the focus of the lab. Oh, goody.
Yeah,
Yeah, we don't want to break the scale. We've had enough scale trouble. Contaminate the cabbage juice and have a real train wreck of an experiment. So we're getting some green in the bottom where the lye is. My hands are slimy from turning my fat to soap where I spilled. And we're still not getting blue.
Do you have a stick?
Do you own a centrifuge?
Well, no, but you can make one out of a salad spinner. But we don't really need one. We have muscle power, right?
And we know this. We are still very pink.
Huh.
It's kind of
This
a
is very
purple color
strange.
now.
Couldn't get enough. Now we've got too much. What a day. Maybe I'll never get blue for you guys. Well,
This
there's
is our
an experiment
green.
at the end of the year where we always get blue out of cabbage juice. Yeah, we have kind of a layer of strange colors. Anyhow, you can see that in the presence of a base, you're going to get greenish or bluish. In the presence of
Or pinkish or purplish.
an acid, you're going to get pink. And if the pH is neutral, if it's neither acidic nor basic, you're going to have purple. So you know that now. That's all good. And we can move on with the real business at hand. The indicator in this lab is only going to serve to show us that a chemical reaction has occurred. I'm going to put this where I probably can't spill it on anything important right now. So it's going to show us that a chemical reaction has occurred. We're not worried that it's an acid reacting and becoming basic or anything like that. We're just worried that a chemical reaction has occurred. So what we're going to do is see if the law of conservation of mass holds true. So leave some space to write your title, your objective, and all of that good stuff, your lab partners, etc. This is just going to be a demonstration. And we're just going to start with procedure.
Do we need to wear glasses? Yeah.
Yes, because I'm going to put lye in it, and it is good form to keep ourselves safe. Next week is the first week I'll do something that is actually dangerous in the sense of shards of stuff could fly through the room. So definitely want to come prepared with your feet covered and,
Do you want us to buy bomb suits?
No. No, if the crucible cracks, it's only this big. It can only go so far.
Should we wear long sleeves?
No. I mean, I think it's okay.
We could bring we could bring sweaters.
The crucible has broken exactly half of the time that I've done this lab in public.
What are we starting with?
What?
Procedure? What are we starting with?
Procedure. So, haven't done anything yet. So the first thing we're going to do is add a little bit of vinegar to the beaker. So how would I write that?
Vinegar was added to the beaker.
Just as a side note, when we're not interested in how much of each reactant we're using, we're doing the lab qualitatively. We're just looking for the quality of what's happening, not the quantity. If we're very interested in exactly how much of this and how much of that, then we're doing the lab quantitatively. The only quantities we're interested in during this lab are that the mass at the beginning and the mass at the end stay the same to show that the law of conservation of mass is being observed. So the second thing we're going to do is put a little bit of, the second thing we're going to do is add some indicator to the vinegar. Alright. Then I'm going to add a little bit of the lye to this little watch glass on the top. So how would I phrase that?
Lye was added to the watch glass on top of the beaker.
Then I'm actually going to use the little stir to stir during the experiment, and so some of the chemicals could still stay on that. So this is my entire system right here. I'm going to move this not so friendly chemical. Okay. Now I'm going to measure the mass of the whole thing. How would I phrase that?
The mass of the beaker, watch glass, vinegar, and stir was measured.
Okay. So we're going to record the mass as, so that would be the beginning mass. Beginning mass will be 175.63 grams. So now we're going to make a prediction. When I mix the vinegar and the lye, a chemical reaction will take place. Unlike baking soda and vinegar, no gas will bubble out. So, when the chemical reaction takes place, what will happen to the mass?
It should not change.
It should not change. Why?
Because according to the law of mass conservation, we should have the same mass at the beginning as well in the end.
Okay, that's the point of the lab, not the fun color change, not anything else. So, when we do the chemical reaction, and the reason that we weigh everything is because sometimes it's hard to get the reactants to go together. So some of these little grains of lye that won't go in will still have their mass recorded.
Oh, we're purple. And
Okay,
now we're
so-
green, really
yes,
fast.
so the distracting color change has now taken place.
I think we just
Yeah, it
skipped
looks
blue
like that
altogether.
Oh, it won't stop sucking it up. Okay. So then we record the mass of the whole system after the chemical reaction has taken place. And the mass at the end is 175.63 grams. Every single atom that was in the lye and the vinegar, now they're not lye and vinegar anymore, but they're still present. So what was my procedure? Not like what we observed, not all of that, but the procedure.
The lye in the watch glass was added to the vinegar and indicator in the beaker.
And then essentially we repeated the step 4, the mass of watch glass, beaker, and stirring rod, and contents where the mass was measured or recorded. Okay. So the mass is going to be the same at the beginning as the end. Yes, so you could have a data section after your procedures. Your data section might have something like the beginning mass, the ending mass, and some observations. So what observations might we have made, or might you have made while we were doing it?
Multiple color changes.
Yep, because
It must be
always the distracting part of the lab. So
in parentheses, distracting color changes.
indicator color was what in vinegar?
Pink.
Pink and vinegar. And what was it at the end?
Green.
Green, yellow. After the reaction. Okay. So that's the important data. And if you didn't put a materials section on this lab, that's fine. If you did, that's fine too. So now we'll write the objective, discussion, and conclusion. So what was our objective?
Check that the math at the beginning of the experiment was the same as the same at the end of the experiment.
To
Good.
prove the law of mass
To
conservation.
support.
We can't prove, we can support. How about compare? Because we're just comparing the beginning mass and the ending mass. So let's go with that. Compare the mass before and after a chemical reaction. So the conclusion should flow right from the objective. So maybe you'll have to write it in later so that your discussion can fit between there. But we could easily write our conclusion now. What would you say? If our goal is to compare the masses, then our result would be
Masses were the same.
the masses were the same before and after the reaction. Now, I will tell you, since we have such an interesting scale today, that occasionally we do have maybe 1/100th of a gram difference. So if we were going to try to explain error, which you guys don't seem to have today, but if we did have some error and you had to explain it away, what would you say?
Breathed on it.
Okay, so if it gained 100th of a gram, maybe some dust fell in it while we were doing it. I would believe that. Contaminant fell in. What if it lost? Like if it had been 175.62 grams at the end, what might have happened?
You could have
Splashed
spelled.
out while you were stirring.
Spilling is the likeliest thing. And I do see a couple of grains here that I spilled while I was doing the fun color change moment at the beginning. I should probably wipe that off real quick so I don't disintegrate my binder or something.
That'd be interesting, chemical reaction.
You would not.
Like the movie.
I disintegrated my lab partner's
I don't think
jeans
it-
several times in class. She was a nice girl.
So she didn't yell at
Sorry,
you?
Julia, if you watch this ever. You were a nice lab partner.
Who didn't yell at you? Probably.
Who still is my friend on Facebook and hasn't disowned me completely. All right, so we've got the main point. Now, when you're writing a discussion for a lab report, what should you always do?
Prediction, errors.
Okay, so we made a prediction and we said we didn't think the math would change, so that's awesome. We should also consult the lab help sheet here and make sure you've covered everything. I just said you don't have to have a materials section if you didn't happen to write one, so it says your report should include all sections. You can ignore the materials section if you need to. So, let's see. You have 4 things in the lab help sheet that you need to cover. They don't have to be in this order. So let's read through them and decide what order we might want to go for here. What was the purpose of the cabbage juice in the experiment, or the indicator in the experiment? Besides the cabbage juice color change, what other evidence of chemical reactions did you observe? Oh, we didn't observe that. I didn't tell you. Actually, you can still observe it. Touch the outside of the beaker downward, but
Okay.
what do you think?
Seems kind of, it seems moist.
That's probably not good. What else do you think? Think of its temperature.
Temperature-wise, seems to be a little warm.
A little warm.
Producing heat.
Okay. So, an evidence of chemical reaction other than the color change with the indicator is that it did have a temperature change. I really need to make a note here to bring a thermometer for that, and that way I will remember to point out the heat
We
change.
can take off our goggles now.
Yes, heat change. But yeah, there's a heat change also associated with acid-base reactions. Let's see. State the law of conservation of mass and explain why the mass of vinegar in lye in containers was equal to the mass of the stuff after the reaction. So, where would you start? What do you think is the best one of those to start your discussion with? Definition? I would definitely start with the definition, but I also might want to start with our prediction. So let's go prediction and then definition. So Micah, you said prediction. What would you say in your discussion to open up?
I would probably say something along the lines of the prediction was that the overall mass at the beginning of our experiment would not change at the end of the experiment. And if there was change, it would be very slight due to error.
So here are some more vocabulary words you guys haven't had yet. Reactants, the stuff that you mix together that undergo a chemical reaction. And then products, the stuff that comes out of a chemical reaction, just so we don't have to go around that. The prediction was that the mass of the reactant would equal the mass of the product. And Lily, that flows right into your definition. So, take it from there when you're ready.
Log. Sorry, which law was that again?
Law of conservation of mass.
Oh, wait. Matter can't be created or destroyed, it can only change form. So it stays the same.
That matter cannot be created or destroyed. So we've covered our prediction, we've covered our definition here. Now we can talk about the color change. What was the purpose of the cabbage juice? And what is the substance that shows a pH change called? or shows pH.
It's called an indicator.
Okay. So why did we use it in this experiment?
To show how lye was a base and vinegar was an acid.
And kind of the key point is it shows that a chemical reaction occurred. And we can just say what it did. We have our observations here. So it changed from pink and the vinegar to yellow-green after lye was mixed. Okay. So an indicator just shows pH, and we could see that there was a pH change. It shows that a chemical reaction occurred. So that covers number 1 on the lab help sheet. Number 2 says, besides the cabbage juice color change, what other evidence of chemical reaction did we observe?
The temperature change.
Okay, so the beaker got warm. Oh, we probably should have written that in the data section too, but we forgot to do it. It was the beaker got warm after lye was added. Which also shows a reaction to state. Alright, so we've laid a lot of foundation on this lab report, but now comes the real point. So lab help sheet on the 4th one, it says explain whether mass of vinegar and lye and containers at the beginning was equal to the mass of the new stuff that was produced. And the lab help sheet says it's sodium acetate and water if you're interested. So, and the containers. So when we mix the lye and the vinegar, the lye, let me see, this does not have to go in your lab report. You can just listen for a second without worrying. Lye is sodium hydroxide. 1 atom of sodium, 1 atom of oxygen, 1 atom of hydrogen with chemical bonds holding them together. Vinegar is acetate, C2. This is vinegar, 4 hydrogens, but I split them up, which I won't explain for a few modules. 2 carbons, 2 oxygens. I'm pretty sure that's acetate. And then it forms sodium acetate. So like this little chunk right here switches its bond to the sodium. And then this little hydrogen and this OH come together, and what do they make? H2O.
Oh.
They make water. So you just kind of break these old molecules into pieces and you form new molecules with them, sodium acetate and water. So that's like what happens, and you don't have to know how to do that at all, but you will. So we literally have every single atom at the end of the experiment that we had before. They just bonded with new friends. Like if I made you two hold hands and 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 you two hold hands, and then I yelled switch and you all ran around and grabbed hands with somebody else, you'd all still be here, you'd just be holding hands with somebody else. That's what chemical bonding kind of is like. Okay, this sodium decided to hold hands with this thing, and then this hydrogen decided to hold hands with this thing, and they formed new bonds. They were all still there. I don't have to rip you in half to hold hands with somebody else. You get to stay whole. And atoms, of course, we can't rip them in half. They stay whole. That's why we have the law of definite proportions, because you can't have half an atom holding hands with something over here for a chemical bond. Atoms have to stay in one piece.